Yes. Start streaming.
It's effectively the whole Microsoft thing. Yeah. Exactly. That's why I haven't paid for it in years. Even though I'm like that.
But I can say, so it's actually free if you're a student.
So then I have to like go through
Yeah.
You know what? I think I played the wrong one. This is the correct one.
So, if you know what the song we played before the lecture, you are probably old enough to capture that TV series that I've been watching before. It's called Ghostbusters, and and I don't think I have to explain too much why we are playing this one because you guys know this weekend is Halloween, and from the personal perspective, I do have a few opinions about Halloween, but so I'm kind of like neutral on that. Part of the reason is because every year I prepare a lot of candies, but not a lot of kids coming in to plant them, and turns out that I have to use them for the next year, which is probably not good for the kids, but at least nobody sued me for giving them those like failed candies, so I think I'm okay. But well, sometimes you're disappointed because you prepare a lot and nobody comes. Part of the reason why I'm not a big fan of Halloween, and well. So, but one thing that I know for sure is like Halloween this year is going to be really different because of the COVID-19 situation. And being honest, I'm not super encouraging you guys to go to somewhere that is really crowded, especially when you go to those like haunted house. People are really close, and people would never wear masks, and people are screaming everywhere, and you definitely know there are a lot of droplets over these places, so definitely not a good idea to go there if you care about your own house or your surrounding house, right? So, and that's the reason why we schedule the midterm on Monday, so that we can make sure that this weekend you will stay at home, stay safe, stay healthy. So, set it aside. Today we are going to continue our discussion on virtual memory, and the reason, the reason why we talk about virtual memory is because memory is such an important abstraction in computer architecture that all your programs, your data reside in memory before your processor can compute it. And previously we talked about, we had a lot of optimizations both in hardware and software to bridging the gap between the performance of processor and memory. And apparently the most important hardware support we have is that we have multi-levels of SRAM caches between the processor and the DRAM-based event memory. And you guys should be pretty familiar with the process of how we access the data for instructions after your homework or after the study, after the lectures last week. And in the last lecture, we also show a case study that, originally you think that the older n-cubic matrix multiplication, you can simply write it as this, well, for sure. However, if you really want to utilize the fact that you have multi-levels of cache, if you want to make them perform as better, then you probably have to rewrite your algorithms like this in a way that, first of all, you should consider transpose your matrices. So when you are performing matrix multiplication, the access pattern will better utilize the spatial locality of both arrays so that you can reduce the amount of conflict misses that you have. And on the second part, you use block algorithm to make sure that every time when I am performing matrix multiplications, I'm only performing them in a submatrix manner in a way that I can reduce the amount of capacity misses and conflict misses for a limited amount of a window. So here is the summary of optimizations that we have been seeing before, right? So before the last lecture, we mainly talked about the hardware optimizations, but for hardware optimization, only prefetch can help compulsory misses, and others can only remedy those missed penalties. So they don't help improve the cache miss rate, which is the main contributing factor of the performance loss. And in terms of the effect of prefetch, I also showed you a demo in the last lecture. It's not as effective as you could imagine because, first of all, prefetch requires your code to be really regular in a way that is easy to predict. However, think about that, right? If you have a data structure that's really random, which most of the time, and that's why, as a computer architect, sometimes I do hate those algorithm or data structure teachers because one thing they love to teach you is linked list. And linked list is a disaster for memory accesses because you can consider the fact that, well, the next node, right? If it's an array, you know it's like the current address plus 8 plus 16 plus 32, something like that. So if you have a hardware prefetcher, super easy to predict. However, if you have a linked list, then where's the next? You only know it, and you can only know it after you fetch the next pointer. And the value of the next pointer, first of all, you need a memory access to it, and the second, there's no clue where it is going to point into. So linked list is actually a disaster in performance, especially for the memory access. So, and that's something prefetch can definitely not help. So, hardware can do very limited things, and as you can start to tell, right? So, how to fundamentally address the memory issue is that the programmer has to adjust their code, making the hardware easy to do their thing. So, what really happened is that, well, if you look at what the software programmer can do, there are tons of things, and all of them are about reduce the misses, right? So if you look at this, if you change your data layout, you can potentially reduce the size of your data structure, or you can change, you can make your data structure more aligned with your access patterns. So it turns out that you can reduce the amount of compulsory misses, you can reduce the amount of conflict misses, or even capacity misses. So everything can be done if your programmer is smart enough to make sure your data layout fulfill the demand of your application. Blocking algorithm in matrix multiplication we just show you, it helps to reduce the footprint of memory access for a short period of time, making sure that we can eliminate capacity misses, conflict misses, and transpose the matrix also help us to eliminate conflict misses because you make sure that your access pattern is better, is more aligned with your memory layout, right? Loop fission is the technique that we break down a single loop into two. So it turns out that within each loop, we only access a limited amount of data, allowing caches with limited weight associativity to perform better. However, if you have a really good processor with multiple ways in memory hierarchy, then what you really should do is that, okay, we can do as many as possible within a loop. So make sure that everything can be done all together to get better performance. Another thing that you can think about is also like loop interchange, right? We demonstrate that through array addition example, and I'm sure there are more examples like that. You can definitely try to think about, well, don't always be too naive about the way how you write a loop. If you think about change the index or the way how you traverse the loop, you can also improve the cache performance, right? So software can do more than you can ever imagine. Then we want to we introduce the idea of virtual memory, and the main reason why we introduce the idea of virtual memory is that in reality, no one or no program is running physically on the main memory. And because the operating system always creates an abstraction called virtual memory for you to run your program. So in fact, after you compile your program counter is encoded in virtual addresses. Your data is also located using virtual addresses. So everything is virtual. So in reality, everything lives in virtual. Sounds very ironic, but that's the truth. So that's why we have to talk about the idea of virtual memory, and today we are going to talk about what architects to do to fix the problem that operating system or software created. So the idea of virtual memory is that it's an abstraction that presents an illusion that you have huge amount of memory, and your program just executes in this comfort zone, and you don't need to worry about how much physical memory installed. You can just use as your wish, and the operating system and the processor will work together to figure out what's the best way to allocate those physical resources. And so here gives you a high-level idea is that even though both programs for both programs they have something with the same memory addresses, but however they are virtual addresses. So turns out that in process A or in process B, even though from a software perspective it's the same address, but in hardware, we are going to redirect it to different locations. So with virtual memory, you can allow multiple programs to share a single limited pieces of hardware, but also allow your program to run even though you don't have sufficient amount of physical memory installed. So because of that, virtual memory is an abstraction that almost every operating system, a feature that almost every operating system has right now. So today we are going to continue about discussion about the virtual memory, and we are going to talk about the architectural support of the virtual memory, and as well as some more advanced techniques to accelerate the abstraction of virtual memory. Originally, I'm thinking about talking about some basic processors, but as you guys would imagine, I don't want to increase the burden of you in preparing a midterm. So today we are only covering the virtual memory part, and the midterm is going to cover the virtual memory part and the topics we talked about before. And at the end of the lecture, I will also briefly talk about what's going to be in the midterm. So pay attention and don't leave before the lecture ends. All right. So we talked about virtual memory in the last lecture, and we talked about the spirit of virtual memory is that the hardware and the software would work together to dynamically remap your virtual addresses to physical memory. So it's really important to figure out how this remap is done. So it turns out that there is a step called address translation in virtual memory abstraction. So again, a very important concept you have is that in modern operating system, the compiler, the operating system, always give microprocessor virtual addresses to you. So your processor would receive virtual addresses from the running code. However, your main memory is located through physical addresses. So you definitely have some translation process to do, right? And don't forget, in virtual address, we organize your address space into pages. So pages are big-sized chunks in your memory space. And typically, in modern operating system, the page size is 4 kilobytes. So you can imagine 4 kilobytes resembles the block size concept you have in cache. In a way that saying that I have a 64-bit address space. What you will really do is that when I access a memory address, I specifically tell the memory system which byte of data I'm located. However, what I need to tell the memory system is what pages am I accessing. So this is similar to the cache in a way that when you access the cache, you don't actually tell the cache which byte specifically. Instead, what you really need to do is that which block are you accessing. So in this way, this is the similarity between virtual memory concept and the cache concept. So okay, so now when you get an address, we are going to partition your address again, right? As I said, right now, all you need is the page number. And if for those of you who are already familiar with the cache idea, you know, well, when we get the the name of a block, or say the tag of a block, we have to eliminate the lower the bits. And how many bits we need to eliminate is related to the block size. And if you have set index, you also have to eliminate that too. And the same thing happens in a virtual memory. However, in a virtual memory abstraction, because it's created by software and people doing software are kind of romantic, they think, well, we love the fact that the page can go anywhere. We don't like the idea that, like the cache, that you restrict the block and go this offset. And you can also consider the virtual page number as a tag in the concept of the cache, and page offset as the concept of offset. So I get the virtual address, I partition them into virtual page number and page offset. And again, thinking about how you access the cache, I ignore those offsets, right? So when you look up the address, you use the virtual page number as the index, to access a huge table, and this huge table contains the lookup result of the virtual page number and give you the physical location of a physical page number, and concatenate that with your page offset. That will be real physical address where your data located. So that's the most simple, naive implementation of page table. You just create a big array of table, and you make each index, each entry in a page table corresponding to a specific virtual page number. This is how you look up. Right? However, it's really problematic, right? So thinking about that, if we have a 64-bit virtual address space, how big the page table is?
I have a question from the previous slide.
Uh-huh.
It mentioned that the content is like all of this is maintained in the OS. Does that mean like how it's stored and
Yeah.
accept
So
changes
it,
with each OS?
yeah, the operating system will decide how the software is going to use the physical memory location.
Okay, so it's how it's used, not like the structure of it.
Well, the structure of it is actually operating system dependent. But I didn't tell too much here because that's actually part of CS203. Yeah, but different operating systems have different structures for the page table. Yeah. All right. So saying that we have this simple naive page table, how big is it? And let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, and look at what you guys think. Ta-da! Wow, definitely we need some kind of discussion, right? So go ahead, discuss with your friend for another 90 seconds.
Yeah, I don't know how to get. Well, each page is for all the and each page is for the language. Yeah, it's 8 bytes. Which is 64 bits. It's going to the entire. No, it's 54 bits. Oh, it's probably not. It's supposed to be petabytes, I remember that. No idea.
All right, it looks like we are about to wrap up. So 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see if peer instruction help us to create a consensus. Woo! Okay, it looks like discussion does help, right? So, looks like a lot of you are cool with the answer of D, but can I have someone explaining it? No idea.
There was a slide in the OS class that said the answer to this.
Oh, what's your whole class? Oh, is that me? Not me? Someone copied my question?
No, he said why we use multi-level.
Yeah, okay, but okay, yeah, but you know, this is not important to get the right answer, but more important to tell us why, right? This is a grad class, we need to know why. Okay, volunteer.
It's guessing at this point, but is it take the page table or the page size?
Multiply it
By the page.
by page table entries.
Yeah.
But how many page table entries do we have? Okay, so one thing that's really important is that, so in our learning curve, I think I should have the same slide for this class, but I do have the same one for the operating system, which explains the educational purpose of this class better. So one thing I do want to say, this is a grad class, right? So it's more important to understand the why behind everything rather than the what. So what's the what? The what is the equation. The why is that why we come up with this equation. So a lot of questions to answers, the answers to the questions will be a lot easier if you know the why. So for example, a lot of you were asking, how do I get the CPI when the memory access latency is really low? And the answer is that, and why we have to times 100% there. The answer is that if you go back to the von Neumann architecture slide, you'll figure out, right? And for this question, it's also the same, right? It's not about what divided by what. It's about why we come up with this, right? So let's go back to this, right? So this is the page table without optimization. So what really happened is that, right, you are using virtual addresses to look up physical addresses. So how many entries do you need to have in the table? Is it related to the total number of virtual addresses or the total number of physical addresses? Total number of virtual addresses, right? So if I have 64-bit address space, what does that mean?
Raised to 64 memory.
What does that mean? Like when people talk about 64-bit virtual address space, what does that mean?
There are 2 raised to 64 unique virtual addresses.
Okay, but why is that? Well, so 64-bit virtual address space means that your address is encoded in 64 bits, right? So you have a total of 2 to the 64 bytes, different combination of bytes that you can express, right? So this is the total amount of bytes you can address in this virtual address space, right? And if we partition this address space by 4 kilobytes, how many virtual pages do we have? 2 raised to 52, but how you get that?
Because we divide
By 4K, right?
total virtual memory by the number of pages.
Right. So exactly the page size.
Oh, yeah.
Yeah, the page size. So if you think about that, right, this is the total amount of virtual pages you have, and it also means that for this table, you need this amount of entries there. Right? So for this amount of entries, if each entry is 8 bytes, that's the answer. Right? So now let's look at the question again. So for this particular question, right, if you have a total of 64-bit virtual addresses, meaning that you have a total of 2 to the 64 bytes of data that you can express, to, you can put in a virtual address space, and each of them is belonging to a 4 kilobytes chunk. So meaning that you have this amount of virtual addresses. And if each of the entry is 8 bytes, then it turns out that you need 32 petabytes just for the page table, right? Don't you see that's a big issue? Do you have petabytes of memory? Do you have petabytes of storage? And virtual page table is just a data structure that we need to locate an address. So you don't even have place for data, even though you have petabytes of memory, right? So if you have a page table like the previous mentioned, it's not going to work. And this is not the worst, right? Thinking about this, this is a page table for just one running process. If you have 32 processes, you have to time this number by 32 because each process means a different page table. So this is not going to work. So how do we make it work, right? So this is the conventional page table, and it's definitely too big, right? You need this way many entries because you want each page in a virtual address space to perfectly map to each of them, an entry in the page table, right? And the other thing is that if you want to facilitate the lookup procedure, you definitely want them to be consecutive. But we don't even have such a big memory, first of all. And even though you have such a memory, you want to find consecutive physical locations, that's almost impossible, right? So this conventional page table idea is not going to work anyway. So how we do it? So the basic idea is that, first of all, look at the real usage of your cases, the case of real usage. If you don't understand that, definitely take CS203 next quarter. So typically when you compile the program, the beginning of the program will be a code segment. And the code segment, as you can tell, that's where you put all your instructions. And then there is a static data section after your compiled program. The static data section are those places if you have global variables declared. So if you have a global variable, the location of a global variable, or even the initial assignment of the values to those global variables will be in the static data section. And then you will have a heap section. So heap immediately follows the static data section. And if you have dynamically allocated data, for example, if you are allocating data from malloc, catalog, or whatever dynamically allocated data, they come from the heap. Or if you have function arguments, if you have local variables, they would be allocated from the end of the virtual memory address space called stack. So this convention is the standard for all programs in at least modern x86 architecture. So you can see for most of the program, only the beginning section and the end section will be used. Right? So turns out this is what happened. Right? When you start running your program, you are starting to consume something from the stack, and you are going to allocate something from the heap, and a huge chunk of the middle part is not used. And even though you have a huge program saying that, well, I have 1 terabyte of data, it's only this amount. It's not even reaching like 1/1000. If you go to Costco, the rate of finding someone with COVID-19 is probably 1/1000 now. And so this, if you even think about this, right? Even use 1 terabyte of data, the amount of virtual memory that you use is actually way lower than that. It's a very little part of the total memory address space, meaning that the huge part it's not used. So if it's not used, why bother allocating entries for that? Right? Why bother allocating entries for that? Right? So this is one trick that we need to figure out how to play to save the size of page table. So here's the idea. We make the page table, instead of a huge segment, we make it also page. So whenever you allocate page table nodes, you break up the page table entries into pages. And each of these entries would, each of these page table entries node would occupy exactly a page. And the reason why we do that is because the operating system, or say again, right, the hardware partition the physical memory location into pages to facilitate management. So if you want to know more, definitely take CS203. And okay, so in this way, right, you can imagine, okay, if each page table node is 4 kilobytes, and if each page table entry is 8 bytes because it's a 64-bit address space, so every address is 8 bytes. So each page table node can store up to this amount of page table entries, right? And for for those you have access, and we know that we need to create a mapping for it, then I dynamically allocate a page to store these entries. And gradually, I will add more entries to the page table, and all by page basis, right? So as you can see, we have more and more pages like this to store those page table entries. However, if you do this allocation on demand, right, what we don't use will not create page tables. Will not create pages to store the page table nodes. So if you create a page table through the page demander and create those pages on demand, those nodes that shouldn't be present will not physically create a page for it. Okay, so now these entries, they are spread out in different pages in a physical location. Another issue is that how can we find out their location? Right? So turns out here is why we need data structure. So B tree, although in general I say like data structure is not that efficient, but I do want to say B tree, if you are not familiar with it, you will figure out it's a very efficient data structure when you want to perform lookup or something else. And it's actually intensively used in database-based systems. So if in your data structure you're not familiar with B tree, I do want to encourage you to go back and figure out what B tree is again. Okay, but the idea here is that we use B tree to create a data structure that for us to facilitate the locating process of those page table entries. So what will happen is that you see that we have a few page table entry nodes spread out in different pages. So we create a B tree structure that makes it easy for us to find out where we treat those pages as leaves of the B tree. And the B tree data structure would help us to easily locate where those leaves are. So this is the idea of hierarchical page table. And this hierarchical page table is actually the most frequently used data structure for page tables nowadays in modern operating systems. Of course, different operating systems have different tweaks on how they use this hierarchical page table structure, but in general, they follow the same idea of making the page table a hierarchical B-tree style like this. So if you read the paper, not sure how many of you did, but I assume if you finished your reading quiz, you already did. So in one of your paper is actually the translation caching, skip, don't walk. And that paper gives you a very good idea about what the page table in use nowadays looks like. So, and as we said, if you want your operating system or your software to run efficiently, it needs the co-working between the hardware designer and the software designer. So one day, Intel and Microsoft, they sit down together and say, hey, we want this, we want the page table looks like this. Intel will say, okay, here we go, right? So, and so in x86-64, here is the way how the page table looks like. And this is the consensus between the hardware and the software. Because if hardware and software both agree this is the way how page tables should look like, the hardware it's easier for the hardware to say, okay, this is how we are going to make the lookup process faster. So in x86 processor, each x86 processor would have a CR3 register. So this CRC register is actually a page table based register that when you change the running process, this register value will be programmed to the physical location of the root node of the hierarchical page table. So as again, the hierarchical page table is a B tree. So you can imagine that this CR3 register will be pointing to the root node of that B tree. So each of the nodes in the B tree contains 512 page table, 512 entries because again, this is 64-bit address, so each address is 8 bytes. So with 4 kilobytes page, you can store up to 512 entries within the table. So each B tree node will contain 512 pointers to the next label. So, but how do I know which entries I should look? So in terms of that, the x86-64 is actually a cheat. They say it's 64-bit address space, but if you look at that, the upper 16 bits, they are used for sign extension, which means that they are not effective. So the biggest lie behind x86-64 is that it's not 64-bit address space. It's only 48-bit address space. And with 48-bit and with the remaining 48 bits, they partition the labels into 5. So the 5 parts of the address, of course, the lower, the least significant bits are the page offset. The remaining parts, they use them as the index to each label of the B tree. And again, because each label of the B tree has 512 entries, so each label of the index also has 9 bits for you to know which entries in the B tree that I should look at. So using this L4 index is 47 bits to the 39 bit, we can locate which entry in the root node that would contain the next label translation of the B tree. So now, in the next label, again, I use this label of index to locate the next label. And when I keep going, reach the last label of the B tree, that's where I can find my physical page number. So that's how we perform an address lookup in this hierarchical picture. Yes? Why they use the sign extension? I think it's just because that makes things easier. Yeah, but not particular other. Because, okay, so the thing is that that's actually a pretty good question, but I think that's somewhat always related. So some of the operating system, they would actually further partition the address space into different bits. And typically, the uppermost bits are considered to have some meanings of the usage of the memory space. So for example, if it's 0, then it's probably like protected. If it's 1, then that's user space. Something like that. Just an example, not necessarily true, right? And if you just store that bit in 48, and thinking about how difficult it is to locate the 48 bits, right? So if what they do is that they put it on uppermost, and typically there are instructions. All you need to do is just to test if it's negative or positive. If it's negative, then like smaller than 0 or bigger than 0. That's easier to test. Right? But if you do it in a different way, that's probably more difficult. Question.
Don't we have permission bits and valid bits, or is that in the page table entry?
It's in the page table entry. Yeah, and thinking about this, right? Even though we have 64-bit addresses, right? Your page offset is not in use. So you have 12 bits that you can put those permission bits in. Other questions? Those are good questions, and those are questions that we can definitely discuss more in operating system class. All right. So, but in terms of a computer architecture, what I want to ask you right now is that, okay, this is the page table we have, right? And you know this page table structure through the paper. So in x86, there is a specific instruction called move that would access. You can consider move as a load. So for this move instruction, how many memory accesses can it create? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Woohoo! Definitely need discussion. Go ahead.
If there are different pages, we have to iterate the outline of
Level.
yeah, but we have to do that for two, right? Oh, so maybe we're there one,
Yep.
another one, goes to four.
Okay.
Although I know it's smart, it's not
Especially like in actions. No. Oh, because assume that there are two completely different pages and none of them are hacked. So then to another, you have to go to access that one. And then to store, you also need to go to a different page outside the storage reserve.
All right, let's wrap up in 15 seconds.
No, you have to read the page table and
5, 4, 3, 2, 1. Time is up. Okay, look at what's after discussion. Okay. All right. Interesting. So what was the question? Okay. Okay. So definitely, what was the most popular answer? Okay. So I guess this is 2. This is 4, 6, 8, 10. Oh. All right. So looks like we don't have a consensus. So this is the process of address translation. And remember what I said in the very beginning. All programs are using virtual address. Right? So, and what's the process of running the program in volume architecture? You guys remember?
we fetch the instruction, then decode it, then execute it.
Okay, we fetch an instruction, right? But before we fetch the instruction, do we know this is a move instruction? We don't know, right? So we have to fetch it. How we encode the instruction address?
With the opcode,
No, I'm saying about the address.
how do we encode it?
Yeah, are we using virtual address or physical address?
Oh, virtual.
Virtual address, right? So we need to look up the physical location of the instruction in the memory. So first of all, we have to access this page table, right? So to access this page table, 1, 2, 3, 4, and with this 4 accesses, you just get a physical address. You haven't get a data or the instruction, right? So you have to access the memory address again to get the instruction. So 5, after 5 memory accesses, we know the content of the instruction, right? And after we see the content of the instruction, as you said, we decode it, we figure out, whoo, this is a data memory access instruction. Okay, how we encode the data memory address? Using virtual address, right?
Yeah.
So we have to look up again another 5, right? So 5 plus 5, the answer would be 10, right? Well, thinking about that, right? If you have virtual memory, turns out that each data access load store would take 10 memory accesses. And remember what? One of the examples that I gave you in the very beginning, right? The memory access time is actually 15 times more than the process. So it means that, okay, with cache, right now with cache, we can cache instruction and data itself. So these 2 accesses, we could make them faster. Right, let's say that this 2 final access to the physical location of the data instruction doesn't incur any penalty. We still have 8 accesses to the page table, and each of them take 50 cycles, 400 cycles. You just figure out the address translation. Does it work out? Right? So here's the thing, right? Operating system is indeed create big troubles for volume architecture. So how do we fix them? Right? So again, we use the idea of cache to store data in instruction. The quick fix that architects come up with is that, okay, we also have a small cache of page table entries to facilitate the lookup. So TLB becomes translation look-aside buffer, right? So it's a cheat sheet of the translation, right? Which is not allowed in the midterm, right? So, well, the good thing about a cheat sheet is that, well, even if this is an open book exam, right? If you put something in a cheat sheet, you don't have to physically turn a book, and you can just look at the cheat sheet. Here's the equation. Right? TLB is something like that. It's a cheat sheet of address translation in a way that whenever I have an address translation, I know the result of the translation. I store it temporarily in the translation look-aside. Right? So if the next time, highly likely, you are going to access the same page, because thinking about each page will contain 4 kilobytes of data, and the fact is that we have spatial locality, right? So it's very likely in the near future you are going to use the same page again and again. So with that translation being captured by the TLB, you don't have to physically go to the page table, right? So this is the first idea. Come up with that, right? So every time when I have a load store instruction, I go to the TLB. The TLB, if fortunately I have some translation of the result, it will dynamically change. It can allow me to change the access and use that address to access your cache. Yes.
Did you say the L1 cache was virtually indexed though?
Not yet. Not yet.
Oh.
Right now. Okay, good. You preview the material. But right now, we are assuming your cache are all in physical memory. Right? Physical memory location are indexed by the physical memory. Right? So this is the first idea we have. Right? We use TLB, translation look-aside buffer. However, as you can see, as what we said, it's really important that I want to make sure that every time when I access memory, the cycle time, the access time are aligned. However, what you do here is that you add TLB in the lookup process, meaning that your cycle time of accessing L1 would be longer because you always add a process of accessing TLB in. So another idea, which is somewhat similar to what you just said, is that, okay, the issue why we have to use physical address to locate data in a cache is because when the cache stores a block, the address of the block, or say the tag of the block, comes from the physical address. So what if we just make the cache use virtual addresses as the tag? Okay, so here comes the idea that this is called virtual cache, right? So we use virtual addresses to access the cache, and then if it's hit, then we can return the block. And if it's not hit, the TLB would give us the translation, and I can use that to access the second level cache or lower memory hierarchy. Right? So in this way, the benefit is that the TLB is no more in a critical path, and it can be accessed concurrently with the L1. However, this is also problematic, not from the hardware perspective, but more from the software perspective, right? Because thinking about this, many applications, which includes our JMOL, they have exactly the same virtual addresses in their program. And we frequently switch context among them. Right? So, which means, or sometimes they are running concurrent. Which means that if you use virtual addresses, there's no way you can tell who owns this virtual address. Right? Like, this virtual address is linked to this application, this virtual address is linked to this application. Now they all come to the cache. First of all, which version should I keep? Even though I have one version, even though I keep both of them, they all have the same address. How can I tell each of them? Right? So the answer is that this idea, does not work. Yes. Okay, yeah, add PID, right? What's the consequence of adding PIDs?
Increase it time.
Well, that's smaller of an issue.
Oh.
I guess that will be
So how long is a PID?
maybe
1 to 64K. So the PID is actually 16 bits. Right? You are adding 16 bits overhead to every cache block. Right? So sometimes it makes the cache bigger, access time longer. From the hardware perspective, is that every bit costs money. So the cost is high. So from Intel or AMD's perspective, we are not going to do it. Okay, so an interesting story, which is a little bit off topic here, but one thing that you can observe is that whenever a software company tries to manufacture the hardware, they never succeed. And the reason is because they ignore the fact that every feature costs money. In software, the feature doesn't cost anything, right? Because your salary to them is so minor, right? However, every feature in hardware costs money. So it turns out what happened is that if you, okay, one good example I can give you is Microsoft versus Nintendo, right? So Nintendo is by no means a software, well, it's a software company, but it's also, it comes from the fact it's a hardware company, right? So they control the cost really well, right? So if you look at the manufacturer cost in the Switch, it's so cheap, right? And Microsoft Xbox is so powerful, right? But they almost sell at the same range of the price. So Microsoft is definitely losing a lot of money on the game console. And the same thing for mobile phone, right? Google Pixel, they have the best spec you can ever imagine. I'm sure it's even better than the best ever iPhone every generation. However, whenever they sell one Google Pixel, they are losing a lot of money. But not the case for iPhone. Apple never sell a phone by losing money, because if you think about where Apple is coming from, in the very beginning, they are just a company manufacturing personal computers from the garage. So it's a hardware company, and they know how to control the cost. So the same thing, right? Yeah, adding the PID would fix the problem, but the hardware cost is not something that any manufacturer, hardware manufacturer, but good answer to that, right? Yeah, adding PID is one of the solutions, but we're not going to do it because it's expensive. All right, so this won't work. This won't work, right? So what's the solution, right? What's the solution? So the thing is that, okay, you really need the physical address to judge if this is the data you want. And adding PID, and another solution that we will mention is like you can flush the cache every time, but you can also imagine that when you have context switch, but you can also imagine the cost. Right? So here it comes with the idea called virtually index physically cache the cache. Well, this is a little bit difficult to understand. I'm trying my best that you understand, but if you don't understand, that's okay. We'll definitely test you during the midterm. But being honest to you, I don't think I totally get it the first time I took the advanced computer architecture class, but it takes me a while to figure that out. But so that's why I'm saying that I totally understand you didn't get it, but let's try our best. Okay, so the basic idea of virtually indexed physically cache is that, again, when we store the tag in the cache, we use physical addresses. But when we try to index where the data might be in a cache, we use virtual address. Remember the process of accessing cache? right? What happened is that you get part of the bits from your memory address as the index. And the index would help me locate the set in the cache. And what you store in the cache is tag along with your data. We use the tag to judge if that's the data we are looking. So if you just want to access the cache, all you need to do is having the index correct. So what if we use virtual address as the index to access the cache? In the meantime, I perform the address lookup using my TLB. Also use the virtual address. So the TLB, in the meantime, it will give me a translation of the physical location, which contains the tag part of your block. And in the meantime, you use the virtual index to access the cache. And the cache, if we store the tag from the physical address, it also gives you the tag area from the physical part. That would give us the right comparison one. Right? Now, the key thing is that, okay, when I serve a miss, I use physical addresses, as you can tell, right? Because I want to use physical addresses to put in a cache block. So the key thing here is that, how can I make the index when I am accessing a virtual address and when I am using the index from the physical address to access the cache would be identical. Right, so here comes the key, right? Remember, when we translate the virtual address, which part remains unchanged? Or say which part is identical in virtual and physical address? Page offset. So the key is that make sure the index field falls within the page offset when you design your memory hierarchy, right? So what would happen is that you carefully design your cache structure in a way that you make sure the block offset and set index fit in the page offset. In the meantime, you perform the table lookup that would give you the physical address. And this physical address serves as the tag. Right? So in this way, you get the effect that I can use virtual address to access the cache. But the output of the tag and the output of your TLB are both in physical addresses. So that I can still use virtual address to access the cache in the first timely manner without dealing with the hassle that I cannot tell who is who. Right? So this is the graphical representation of the whole process. Hopefully that will help you better. So we get the virtual address. We partition the address into block offset and set index and virtual page number, right? And remember here, set index and block offset, they represent the page offset as well, right? So you don't need to worry about it, right? And the virtual page number can be used to access the TLB. And you use the set index to access the cache. And in your tag, you also store the physical page number. So in this way, as long as the TLB lookup result is consistent with your tag, it's a hit. And you know this is the data I'm looking for exactly for sure. Right? And they are in parallel. What a beautiful. This is really beautiful, right, in terms of architecture design. So, with virtual, so now you might be asking me a question, right? Is there any drawback of that? Right? So no free lunch. Here's the drawback. Right? We just say that you have to carefully organize your cache in a way that your block offset and set index fitting the page offset, right? So if you remember C equal to ABS, what that really says is that your log B plus log S must be equal to 12 or even smaller than 12. Now, use a little bit of math, right? C equal to ABS, and this is log 2, and I believe you probably learned this kind of math in high school, is that if you restore the log, and you know that if log B plus log S equals to 12, it means that B times S is 2 to the 12. If you don't know what is this, not my fault, your math teacher's fault. Okay, so using that equation, right? So you see that the equation of CABS is really powerful, right? So it means that C equal to 8 times 2 to the 12. So if you only have a direct math cache, the available cache size is only 4 kilobytes. We can only build very small cache. Yes. So now I have a question for you. If the operating system use 4 kilobyte pages, and if you want to build a 32 kilobyte cache with the restriction that you want virtual index, physically text cache, what's the block size? What's the assumption? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Definitely we need discussion. So go ahead, discuss with your friend.
I had C and ABS. And we know that the task size is, and we know the set size is 2 to the 15 over 2 and 12, the base size is 2 to the 16. 8 times 3. So we divide the base size by the capacity by base size. That's the set. Yeah, you're right. Yeah, 2 to the 12, and then this is number of pages. We have 2 I got C. No, but sets and pages are like setting.
So I don't know that.
Because like maybe.
Oh, yeah, yeah.
Sometimes. Oh, let's see.
All right, looks like it's getting quieter, so let's wrap up in 15 seconds. Oh,
Because S is number of sets. Then we know the content.
5, 4, 3, 2, 1. Time is up. Okay, after discussion, what? Whoa, like a ladder, and D seems to be most popular. So, can some of you tell me about how do you? Okay, you volunteer.
Wait, but I got C.
You got C. Okay. So, but how do you get C?
Okay, so I use C equals ABS.
C equal to ABS. And you know that for the BS, I'm not saying something, right? For the BS, it's 2 to the 12, right?
Yeah.
And
And the capacity is 2 raised to 15.
2 raised to 15. Why?
Because.
Oh, yeah, 2 raised to 15, right?
Yeah.
So what's the A?
Wait, we still have AB. I haven't made a conclusion about the B yet. Block size. I didn't make conclusions about block size yet. Wait, how did we get B yet? Oh, it uses 4K pages, so it's 12.
Okay, so let's say, right, if you have 215 equal to, say, A is the unknown, and you assume it's a 64 byte block,
Wait, is
right?
it block size also unknown? Oh, okay.
No, the block size, well, so here is the possible potential answers. So if this is the block size, right, it also means that the number of sets you can have is 6 because you need to follow the restriction that it has to be 12.
Yeah, but then you can't use 4K pages.
Right, you cannot use 4K pages, right? So the A here must be 8,
Yeah.
right? So which option fulfills this?
Oh, D.
D,
Yeah.
right? So that's how you get D, right? Because D is the only possible option. And in fact, if you are familiar with those configurations that we have told you before, right? 32 kilobyte, 64 byte block, 8 way. Is it familiar? Have you ever seen this configuration somewhere?
That's on your computer, right?
That's how Intel and AMD processors L1 data cache looks like. Right? So what does that tell you? Modern processors, they configure their own cache. Why they only have 32 kilobyte L1 cache? Because we have to make it virtually indexed and physically tagged. That's why it is, right? And that's the reason. That's the why. Another evidence that they are using virtually indexed physically tagged. Question? Yes, but yes, I think it will still work, right? But 32 byte block, right? What's the drawback?
One block size more.
The more compulsory method. Right? So that's the issue, right? So that's the best outcome they can come up with. So there are tons of reasons why modern processors they all end up with a similar cache hierarchy design. Because there are tons of architectural choices that turns out that's currently the optimal. Okay, so we don't have time to go through some of the interesting stuff that I really want to share with you. But okay, one thing that I do want to mention is that if you read the paper Efficient Virtual Memory for Big Memory Servers by Mark Swaib, Mark D. Hill, well, these guys, they are all really famous now. So this paper is actually saying that, right? If you remember, if it's a page table, we need to go through the process of translation. And there is another way you can actually make the translation easy, is that if everything is consecutive, all you need to do is a base address plus the offset. However, the most important assumption here is that you can find consecutive address at physical location, right? So we may not be able to do it with machines with small memory or a machine with uncontrolled memory. So, but if you have a GPU, right? If you have a GPU, it's possible. So, if you are familiar with GPU programming, you know GPU, you can also use CUDA-malloc, and it's also giving you a virtual address. However, this virtual address is actually coming from the fact they are actually segments in the GPU. So what happened is that in their runtime, they just record the starting address of the physical memory segment in a GPU. And instead of using a page table to look up the address because it's really slow, and there is no hardware support for GPU address translation, in this way, it's making things faster. Is that and GPU, they have a controlled runtime. And the other thing is that because we typically want to use GPU for big data, so you tend to allocate huge data structure in GPU. So it turns out it's easy for the GPU to do segment in a way that you just record the base address, and this address will map to a certain physical location in the GPU, and everything is consecutive after that. So that's the important implication that I encourage you to look at the run segment. Now, the most important thing that you guys care about is the midterm. So logistics is about the midterm. Expect you have 15 multiple choice questions, and they are similar to your Paul reading quizzes, and short answer questions times 4. There will be homework style question times 3, and again, you won't receive any credit if we only see the numbers, so definitely want to explain how you come up with that. And again, the reason why we have that is because this is a grad class. We care about the why more than what and how. Okay, so sample midterm. So this multiple choice questions you can go through, and we have short answer question, and it's called short answer question. So I do want to make sure that it's short enough when I see the exam. So make sure that each of your answer is smaller, less than 30 words, fewer than 30 words. If it's over 30 words, I'm not giving you any credit. It's 30 words. And it's really important because, you know, it takes time for us to grade. If you make it long, right, you are torturing us. So make sure these are short answer questions, and I will pick questions from this set. So you are prepared. Your 30-word question answers. All right? Be well prepared how to make sure answer each of these in 30 words. 30 words. 30 words. Okay? More than that, I'm not going to grade it. All right. Pre-answer question and also is important. You have that kind of question in your homework. Speed up is important. You have that kind of question, right? Performance evaluation in assignment 2, right? I love it. You love it. And cache simulation, we spend a lot of time in it. So it's not too difficult to guess. That will be on your midterm. Other than that, don't forget to turn in your assignment tonight and midterm next Monday. And you saw the sample midterm is going to be with the slides today. So, and I will try my best to upload the slides within an hour after the lecture. So don't urge me on Piazza. I'm trying my best to help you, right? You may review and focus on the material covers in lectures, and you should also review your assignments. We will publish the solution immediately after every deadline, and that's the reason why we don't set late submissions, because everyone who submitted homework wants to see the solution as early as possible. you are delaying your submission, which means that you are hurting other people's rights in seeing a solution early. So we don't accept any late submission. And the material today will be included in midterm, as you can see. Again, I promise you, I will let the project out by the end of the week. The end of the week means 11:59 on Saturday. I will try my best. All right. Other than that, enjoy the rest of your. Yes, question. When is the project submission? I don't remember, but it should be somewhere
End of the quarter, right?
end of the quarter. But I think it's due last week, the last week of the quarter. And again, the project is a competition, so give us some time. It definitely cannot be the last lecture, because what I will do in the last lecture is that I will give the champion an award of Amazon gift card, right? So that's why some of you last quarter keep staying in my class, because you guys know that for this class, not only you can earn grades, you can also earn gift card. All right. Other than that, enjoy the rest of your week. I will see you next Monday. Oh yeah. Oh, you're black. Oh, yeah. Yeah.